evaporators, and cooling towers, and so many things like that. Okay, all these things will come under this heat exchangers. Okay, so all the processes in industry will involve heat exchange basically, but heat exchange between the fluids, in specific, we call it as heat exchanger. Okay, so to give an example to you, we basically have two types of heat exchangers. Okay, first one is a parallel flow heat exchanger. I'm drawing it here, as you can see. And the fluid is entering here like this in a tube in tube kind of a concentric tube heat exchanger. Okay, and the fluid is flowing in this direction in the annulus, and fluid is also flowing in this direction in the inside tube. Both fluids are flowing in the same direction. Both fluids flowing in same direction. So that's why we call this as parallel flow heat exchange. Parallel flow heat exchange. Right? So what is the next one? The next one is your counter flow heat exchanger. Counter flow heat exchanger. Okay, again, here you will have the same kind of figure. Okay, on this side also. But what is the difference here? Here, one of the fluids will be flowing in the opposite direction. That is the difference here. If one fluid is flowing in the opposite direction, then you call it as a counter flow. Okay. So here fluids flow opposite to each other. Right? Now, here I would like to draw a temperature profile of this fluids here. Okay, let me take red for the inside fluid. Okay, see, if this is a parallel flow, what will happen to the temperature of, let us say, okay, cold fluid is flowing here in the inside one, or hot fluid is flowing in the outside one. Anything you can take. Okay, cold here, hot there, doesn't matter. Okay, any one you can take. So if it is flowing inside, what will happen to the temperature of cold fluid? Tell me whether the cold fluid temperature will increase or decrease.
Increase.
Cold fluid temperature will increase. So this is the increase I am showing. This is the increase. Cold fluid increase in the temperature. Okay. Next, hot fluid. What will happen to the hot fluid temperature? What will happen to the hot fluid temperature? Whether it will increase
Increase.
or decrease? Huh? Somebody is saying,
Decrease.
say, it will decrease. Okay. It will decrease. So basically, this is the inlet point, and this will be the outlet point. Okay, so when the cold fluid is entering, let us represent the cold fluid temperature with the small t. I am following this nomenclature because the same has been followed in the data book. So inlet he will call it as 1, and cold fluid temperature for outlet he will represent with 2. Okay, and coming to the hot fluid, he is representing it with capital T and 1 with inlet, capital T and 2 with the outlet. So this is how the things are represented, right? So it is important to note that I have not drawn this particular hot fluid temperature in this way. Okay, I would have drawn it like this. This is also a decrease. Okay, but this is not correct. Okay, that should not be done like that. Why is not done like that? Tell me. Please speak out. See, essentially what's happening here is hot fluid will exchange the heat with the cold fluid. Cold fluid will lose the heat to the uh, hot fluid. So what's happening is from hot fluid, heat is flowing to the cold fluid. In the process, hot fluid is getting colder and cold fluid is getting hotter. Okay. As this process happens, the hot fluid temperature cannot come below the cold fluid temperature, or the temperature of the cold fluid will not cross the temperature of the hot fluid. Okay, because they may reach this point, that is thermal equilibrium point, but beyond this thermal equilibrium point it is not possible. Okay, that is a impossible process according to the laws of thermodynamics. Okay, so this is to be kept in mind. That is the temperature profile variation in case of your parallel flow heat exchanger. Moving to the counterflow heat exchanger. Moving to counterflow heat exchanger. Let us draw the temperature profile here. So if it is counterflow heat exchanger, tell me what happens to the hot fluid here. You can take hot here, you can take cold here, and you can take the reverse way also. Anyways, okay, hot and cold. So tell me what happens to the hot fluid temperature. See, whatever may be the case, the temperature of the hot fluid will decrease. Okay, because it has to lose heat to the cold one. So this is the hot fluid temperature drop. This is the hot fluid temperature drop. Okay, this will be your inlet for hot one, and this will be the outlet for the hot one itself. Okay, so next tell me what happens to the temperature of the cold one. Yes, please speak out. What happens to the cold temperature? See, for cold one, the inlet will be on this side. This is the cold inlet. Outlet will be here. So if I have to draw, I have to start from this side. Okay. When I start from this side, what happens to the cold one temperature? It will increase because it is cold. It is take heat from the hot one. Its temperature will increase, and this will be the direction of the cold one. So here you will get small t1. Here you will get small t2. That's the difference here. Okay. So next comes the concept of LMTD. LMTD means logarithmic mean temperature difference. Okay. So if I have to say this LMTD in case of a parallel flow, how it will be, and in case of counterflow, how it will be. See, for this, you will take delta T1 here. This delta T1 is the difference of capital T1 minus small t1. That is the delta T1 on the left. Then I will take delta T2 on the right. Let me write it below. If I take delta T2 here, it is capital T2 minus small t2. Okay. So what's happening here? You have delta T1 on one side, delta T2 on the other side. So that the LMTD will be equal to delta T1 minus delta T2 by ln delta T1 by delta T2. ln meaning logarithm to the base e. Okay. So this is how the formula is taken in case of a parallel flow. In case of a counter flow, what varies is only delta T1 and delta T2 varies. The formula remains the same. This is the formula for both parallel and counter. Only the delta T1 and delta T2 varies. So here the delta T1 will be equal to capital T1 minus small t2. Here delta T2 is equal to capital T2 minus small t1. This is the delta T1 and delta T2 in counter flow. Okay. So only these things changes for LMTD. Okay. Apart from this LMTD concept, you should also have an idea of what is overall heat transfer coefficient. Overall heat transfer coefficient. So if we take this overall heat transfer coefficient here, for this, let me take this heat exchanger here. This is the outer tube of the heat exchanger. Also, there is an inner tube for this heat exchanger. So inside, one fluid is flowing and outside one fluid is flowing. Here you have cold fluid, here you have hot fluid, something like that. Okay. So fluids are flowing here. Let me call this as inside and let me call this as outside. Actually speaking, this space is annulus. Proper way of saying it is annulus. That is the space between your inner tube and outer tube is called as annulus. So in and out is good enough. So it can be hot or cold, cold or hot, anything, it's okay. Now, if I have to draw the resistance circuit for this, how it will be like your composite cylinder concept. Okay, this we have already seen in the second unit. Tell me how to draw the composite cylinder thing here. Please speak out. Resistance. So there will be basically three resistances. Resistance due to convection inside. Okay, you have a fluid flowing here in the inside that will contribute for R convection inside. Now let's move to the second one. Okay, what is the second resistance here? The second resistance will be the resistance due to the conduction provided by this inner tube. And then I'll have one more convection resistance, and this convection resistance is provided by the outer fluid. This is how the series connection will look like. So here R equivalent will be equal to R convection in plus R conduction plus R convection out. So R convection in, if I have to show, so what is the formula? Tell me. What is the formula for resistance? Convection resistance. Please speak out. It
1 by
is
H.
simply 1 by HA. H inside and area inside. Then what is the formula for R conduction here in the case of cylinder? 1 by 2 pi KL into Ln, higher radius by lower radius, R outer by R inner by 2 pi KL I'm writing. Generally write it like 1 by 2 pi KL into Ln, R by R. This is also the same thing. Okay, R conduction is over, then R convection out will be 1 by H again. It is due to convection again. So this is H outside and area outside. Okay, so that is the thing. Now, if I have to write for the Q effective for the heat exchanger, what will be the formula? Please speak out. It is UA LMTD. Okay, see it is taken in parallel to your Q is equal to HA delta T. In place of delta T, we have brought in this concept of LMTD. Okay, so in a heat exchanger, there will be 4 temperatures whose effect has to be taken into consideration. So you cannot accommodate those 4 temperatures in one delta T because delta T can accommodate only 2 temperatures. So we are going to the concept of logarithmic mean temperature difference. Okay, so here also temperature difference is taken, but it is taken as a difference on one side minus a difference on the other side. Let us see. Here I have shown it to you. Difference on inlet side and difference on outlet side. One side versus other side. Okay, that's why delta T1 minus delta T2 concept came into your LMTD. Okay, to get the overall effect properly, actually here logarithm is taken because the kind of variation that you can see here is it's a curvy kind of thing, and it's a kind of logarithmic variation. Okay, so that's why logarithms will help you. Logarithmic variation will help you, quantify this difference appropriately. So that's why in place of delta t, we will use LMTD here, and it has been proven experimentally that LMTD is going to give the correct value of heat transfer, the predicted value and the experimental value both will match if you use LMTD. Area anyways is the same. In place of H, you will be using the U, that is overall heat transfer coefficient. Okay, so that's how you got this concept of Q is equal to UA LMTD. Okay, so now if I have to tell the resistance of heat exchanger, overall resistance of heat exchanger, that is a R equivalent is equal to what? Tell me, using this formula, what will be the formula for equivalent of heat exchanger? It is 1 by UA, like it is 1 by HA for convection case. Here it is 1 by UA. So what I ultimately got here is essentially this: 1 by UA is equal to 1 by HIA plus ln R by R by 2 pi KL. This is R outer by R inner plus 1 by H outer and A outer. Okay, so this is the formula here. Okay, so if you want to find out U, that is the overall heat transfer coefficient for any given heat exchanger, this is the procedure that you will follow. Okay, so this can be actually simplified to even simplified way. See, if you look at this R values of, that is this R O, and if I zoom it here, okay, it will be something like this. This will be Ri, this will be Ro. Okay, so the thickness of this tube will be very small. That's why Ro is almost equal to Ri. So if Ri is equal to, if Ri is almost equal to Ro, then what happens? Your equation will be like ln1. Ln1 is 0. So this value can be neglected. R conduction is almost equal to 0. Okay, so the effect of this conduction, the resistance due to conduction can be neglected, and it means in the practical things also, because if you choose very good thermal conductivity material, the temperature difference is also very less. When the temperature difference is also very less, the resistance also will be less. The thermal conductivity is more, the thermal resistance will be less. So if this thermal resistance is really less, you can definitely neglect it. So what happens to this equation then? Then it will turn out to be 1 by UA is equal to 1 by HI AI plus 1 by HO AO. This is the simplified form of it. Okay, if you take furthermore simplification, that is area outer and area inner are almost equal to the overall area, then this equation will turn out to be 1 by u plus, sorry, 1 by u is equal to 1 by u is equal to 1 by hi plus 1 by ho. That is, the areas are taken out here. Okay, so that's how you take the formula for overall heat transfer coefficient. Okay, based on the situation, you can choose which formula to be used. Based on the given data in question, you will be choosing which formula to be chosen. Okay, apart from this one, there will be something called as fouling. Okay, fouling means what? See, as the water is flowing for so many days on the given tube, what happens is there is a formation of scaling here. Okay, so scaling can be formed here, here, and here also the scaling can be formed. Okay, so this scaling will result in something called as a fouling resistance. Okay, so this one will offer again one more resistance. If the effect of it has to be considered, how do I take it? Fouling resistance concept. If I take it, so your R equivalent, that is 1 by UA, will be 1 by H IAI plus Fi by AI plus ln R O by Ri by 2 pi KL plus FO by AO plus 1 by HO by HOAO. Okay, this is your equation when you consider the effect of fouling here. Okay, in this, what will be your F? Tell me. F is nothing but a fouling factor. Okay, fouling factor is value which will vary based on the kind of metal and fluid. For a metal and fluid, the fouling resistance will vary. So for a copper and water combination, you will have so and so. Like that, you will have fouling resistance, and this fouling resistance is measured in what unit? Tell me. Look at the equation and tell me what will be the unit of F. Kindly speak out. See, it will have inverse unit of your H. H is watt per meter square Kelvin. So it is taken in the numerator. So it will have inverse unit, that is meter square Kelvin per watt. So that's how your fouling factor is taken. So that can be taken into the consideration and the calculation can be done. Okay, so that's the thing regarding fouling factor. Now straight away let's move to the problems. So here I have one problem. Let's solve it. Uh, so this is the problem here. In this problem, what he is saying, first he say determines. Okay, first thing to do here is to find out what kind of heat exchanger it is. He is saying that it is parallel flow heat exchanger. So that is the first thing here. It is a parallel flow heat exchanger. Okay, once you know that it is parallel flow heat exchanger, you will be in position to solve it. Then he is giving the temperatures here. Okay, so heat exchanger to cool oil from 60 degrees centigrade. Okay, so cool oil, he is saying. So cool oil means, is this a hot fluid or a cold fluid? Tell me.
Hot fluid.
Hmm? It is taking from 60 degrees centigrade to 30 degrees centigrade. It is saying that it is a cool, means it is to cool. Its function is to cool oil. Okay, so the whole heat exchanger will do this one. So this 60 and 30 degrees centigrade, whether these are the temperatures of a hot fluid or cold fluid, we have to look at. Okay, using the water available at 20 degrees centigrade, 20 degrees centigrade, outlet temperature of the water is 26 degrees centigrade. See, here looking at the values itself, you can say which one is hot and which one is cold. See, if you look at these two temperatures, this is hot one. If you look at these two temperatures, you can say this is cold one. Okay, so this is given for oil and this is given for water. So write the temperature, look at the values of temperatures, you will understand which one is hot and which one is cold. Okay, then if it is hot, what is the nomenclature that we take? Capital T. Okay, if it is cold, what is the nomenclature we take? Small t. Okay, so if it is entering, what is the temperature? Oh, nomenclature 1. If it is leaving, 2. So this is capital T1, capital T2. So hot water is available at 20 degrees centigrade, so it is entering with 20 degrees centigrade and it is leaving with 26 degrees centigrade. Entry we will write 1 suffix and exit we will write 2 in suffix. So this is how nomenclature is taken in your data book. That's why I'm using the same thing here. Okay. Apart from this data, what is given? The rate of flow of oil is given. Okay, m dot of oil is given as what? 10 kg per second, and specific heat of the oil, Cp of oil, is given as 2200 joule per kg Kelvin, and overall heat transfer is given in question. Okay, U is given. See, in most of the questions, U will not be given. Anyways, in this question is given watt per meter square Kelvin. You have to find your U if he is giving you the diameters and the whole stuff. So, anyways, U is given. Also, he is saying that compare the area required for a counterflow heat exchanger also. So, you have to solve the same problem for counterflow heat exchanger also. Okay. So, essentially, he is asking you to determine the area. Okay. In the beginning of the question itself, you can say determine the area required. All right. So, this is the question here. So what to do next? You can draw this temperature profile here. The hot fluid will be like this for a parallel, and cold fluid is this one. On this side you have 60, on this side you have 30, on this side you have 20, on this side you have 26. See, if I write these values here, they should make sense here. Okay, 60 is reducing to 30. That's right. Correct. 20 is increasing to 26. That's correct. And your 26 should be less than your 30. That is also making sense here. So overall, it is making sense. If I have to measure delta T1 here, what will be the value? It is something happened. What will be the delta T1 here? It is 60 minus 20 on the left hand side. On the other side, the delta T2, it is 30 minus 26. So tell me what are these values. Delta T1 is equal to 60 minus 20 is 40, and delta T2 is equal to 30 minus 26 is 4 degrees centigrade, or this is also equal to, since this is delta T, this 40 Kelvin also. Both are equal, 4 Kelvin. Anyways, so you have done these delta T1s here. So what is the next thing to do? You have to find out the LMTD. LMTD is equal to delta T1 minus delta T2 by ln delta T1 by delta T2. So this will be equal to, the delta T1 value is 40 minus 4, that is the delta T2 value, by ln 40 by 4. So tell me what is this value of LMTD quickly.
15.6346.
Huh?
15.6346.
15.634. What is the unit of this one, LMTD? What will
Degrees
be the unit of LMTD? You can take degree centigrade or Kelvin also. Both are okay, both are equal. Okay. So you're done with LMTD. So what he's asking you to find actually is actually finding asking you to find area. So if you want area here, Q is equal to UA LMTD. Okay. So this LMTD value is known to you. U value is given in question. Area value is unknown. So what you should know? Q you should know. So how to get Q here?
MCP delta T.
You can simply use Q is equal to MCP delta T on any one side, either on hot side or on cold side. But here M is given for only one side, that is for hot fluid side only, that is oil only it is given. So you have to use oil values here. M oil, CP oil, delta T of oil. So M oil is given as 60 kg per second in question. Correct kada? M and icharu 10, it is not 60, it is 10 kg per second, and Cp value is given as 2200, and the delta T is 60 minus 30. So tell me what is the Q value now?
660 kilowatts.
60 kilowatts, huh?
660, sir.
660, so it's like 1, 2, 3 watts. Okay, this many watts, you got it. Okay, this is the Q value. So substitute all these values into the Q is equal to UALMTD. Then you will have area. Area is equal to Q by U into LMTD. The Q value is 66 by U value. U value is 300. What is the LMTD value? 15.634. 634. So tell me what is the area? Quick. Stefan, area. Area anthem. Please calculate and tell me. Meanwhile, I'll proceed to the counter flow. Heat ex
140.71.
140.71 meters square. That is the area. That's what he's actually asking you to find in the question. Fine. So now let us take the counter flow heat exchanger question. Okay, if I take this counter flow heat exchanger question, it is like, so how is the temperature profile here? It's like this. The hot fluid temperature is decreasing and the cold fluid temperature is increasing. It's like this. So here from 60 it is moving to 30. Here from 20 to 26 it's moving. See, even now it should make sense. Okay, 30 is greater than 20, 60 is greater than 26. Okay, so all these temperatures should make sense for you here. So that's one thing. So this is the direction. You can see that they are moving counter to each other. So if I have to write the delta T1 on the left here, what is the formula? What are the values? Delta T1 is 60 minus 26. Here delta T2 is equal to 30 minus 20. So here the value is 60 minus 26 antedi. And so simply LMTD I have to calculate here. That is equal to delta T1 minus delta T2 by ln delta T1 by delta T2. So that will be equal to 60 minus 26 minus 30 minus 20 by ln delta T1 is 60 minus 26 by 30 minus 20. So what is the LMTD value?
19.61.
What?
19.61 degrees centigrade.
Yeah, 9.61 degrees centigrade is your LMTD here. So if you want A here, the formula is Q in by U into LMTD. So Q value is 6. This one I've already found out previously. U value is also given in question, and the U value 300.
300.
And LMTD just now found out it is 19.61. Tell me what is the area value?
1
112 point.
112.18.
AC is equal to 112.18. So this is the thing. So this is what he has asked you to find. Okay. Apart from this, you can also find the other things also here in this question. Like he did not give you what is the value of um, fluid flowing in the colder thing. Okay, MC value is not given. So sometimes that question also can be asked, or that may be required for you. So he may ask you like what is the Q on cold side, heat transfer on cold side. Okay, for that also you need MC actually. So that sort of question also can be asked. So Q cold is equal to MCP into the delta T. Okay, on cold side, whatever the fluid is there, same things we have to take for all the things here. So what is Q cold here? Is it known to you in this question? Hmm? Speak out.
No.
See, it's not like that. Okay. If you take energy conservation, Q cold is equal to Q hot. That is, whatever the heat that is lost by hot one is taken by the cold one. Okay, that is law of conservation of energy, first law of thermodynamics. So Q cold is equal to Q hot. So that's what uh, conservation we take. So Q cold place you can put like m dot c into cpc into delta t on cold side is equal to q hot. Q hot is known to you in this particular question. So substitute the values. M dot c is unknown. The cpc, is it known to you? Cpc, tell me.
4180.
Yeah, for water it is 4180. You have to remember. Okay, for water the cp value is 4180. Or you can go to the data book page number 30, you can get the cp value also. Okay, so that is the thing regarding the cp. The delta t is given for the cold 26 minus 20, you know it. The hot fluid, it is 60 to 3. So m dot c is equal to something, you can calculate and tell me. Anyways, you can calculate for yourself. Okay, so which one is to be preferred is a important question here. Preferred heat exchanger. Okay, whether you will take parallel flow or counter flow. Tell me, రెండిట్లో ఏది మంచిది? ప్యారలల్ ఫ్లో మంచిదా, కౌంటర్ ఫ్లో మంచిదా చెప్పండి. ఏది తీసుకుంటే మనకి ఎక్కువ లాభం?
Counter.
కౌంటర్
Parallel.
ఫ్లో.
More
వై
area.
కౌంటర్, వై కౌంటర్, వై ప్యారలల్?
More area and contact.
You can look at the area values here. Area for the parallel and area for the counter. చెప్పండి ఎంత వచ్చాయి? In the question, parallel flow 140 వచ్చింది మీటర్ స్క్వేర్ అప్రాక్సిమేట్ గా. ఇది కౌంటర్ ఫ్లో నేమో 112.18 అనుకున్నాం. సో ఏరియాస్ చూడండి మీరు. In counter flow, for less area, it is creating the same effect. Same heat transfer is happening in counter flow with less area. Okay. and for creating the same effect, the parallel flow is taking a lot of area. So what happens is, if your area is increasing, your cost is increasing. So area is increasing means you have to increase the size of your tube. When you have to increase the size of your tube, obviously cost will increase. So most of the times your counterflow heat exchanger is preferred. Why? Because counterflow heat exchanger is creating the same effect of the parallel flow with the less area compared to the parallel one. So that is a good thing regarding your counterflow. So keep that in mind. So in the next class, we will solve problems using the data book itself. All right. So I hope it's clear. There are a few more cases in this one. Let us see all that in the next class.